At the beginning of the 20th century, physics seemed almost complete. Classical mechanics explained the motion of planets and everyday objects, while Maxwell's equations elegantly described electricity, magnetism, and light. Yet, there were cracks in this seemingly perfect foundation. A small problem loomed on the horizon, one that would eventually shatter classical physics and usher in an entirely new understanding of reality. This was the blackbody radiation problem, a puzzle that classical physics couldn't solve. Blackbody radiation refers to the spectrum of light emitted by an object when heated. Imagine heating a piece of iron. It first glows red, then orange, and eventually white as its temperature rises. Classical theories predicted that objects should emit infinite energy at high frequencies, creating a catastrophic paradox known as the ultraviolet catastrophe. Experimentally, however, this didn't happen. The energy radiated was finite, and its distribution followed a curve that classical physics couldn't explain. This wasn't just a minor inconvenience, it was a direct challenge to the laws of physics that had governed science for centuries. In 1900, Max Planck, a German physicist, stepped forward to address this crisis. Planck wasn't looking to revolutionize physics. He simply wanted a mathematical solution to fit the experimental data. He proposed something radical. Energy is not emitted continuously but in discrete packets, which he called quanta. To understand this, imagine pouring water into a glass. Classical physics treated energy as if it flowed like water, smooth and continuous. Planck, however, showed that energy behaved more like marbles dropping into a cup, separate and indivisible. To quantify these energy packets, he introduced what we now call Planck's constant, a fundamental constant of nature. Planck's theory worked beautifully, solving the blackbody radiation problem. Yet, even Planck himself doubted the deeper implications of his discovery. He viewed his quanta as a mathematical trick rather than a fundamental aspect of reality. Little did he know, his idea would spark a revolution. Soon, other physicists would take his concept and push it further into realms he couldn't have imagined. One of those physicists was Albert Einstein. While Planck had quantized energy, Einstein extended this idea to light itself. In 1905, Einstein proposed that light is made up of discrete particles called photons, each carrying a specific amount of energy based on its frequency. This wasn't just a theoretical leap, it solved a long-standing mystery called the photoelectric effect. When light strikes certain metals, it ejects electrons. Classical physics couldn't explain why only high-frequency light, like ultraviolet, worked regardless of intensity. Einstein's photon theory provided the answer. Only photons with enough energy could knock electrons loose. Einstein's work earned him a Nobel Prize and confirmed that light behaves as both a wave and a particle, a duality that defied common sense. This wave-particle duality became one of the cornerstones of quantum mechanics. It was the first hint that the rules governing the microscopic world were fundamentally different from those of the macroscopic world we experience every day. As physicists delved deeper into the quantum realm, they discovered more strange and counterintuitive phenomena. One of the most famous is Heisenberg's uncertainty principle, which states that you can never simultaneously know a particle's exact position and momentum. This isn't due to limitations in our measuring instruments, it's a fundamental property of nature. Imagine trying to pinpoint the location of a marble on a vibrating floor. The harder you focus on its position, the more its motion becomes unpredictable. This uncertainty is not just a quirk of quantum mechanics, it's a defining feature of the universe at its smallest scales. Another bizarre aspect of quantum mechanics is the observer effect. At the quantum level, particles exist in a state of superposition, meaning they can be in multiple states simultaneously. However, the mere act of observing a particle collapses this superposition into a single state. In other words, the act of measurement changes the system being measured. This phenomenon challenges our understanding of reality itself. How can something exist in multiple states until we look at it? Does reality depend on observation? These are questions that physicists and philosophers are still grappling with. The deeper scientists probed, the stranger the quantum world became. Erwin Schrödinger, one of the pioneers of quantum mechanics, illustrated the weirdness of superposition with his famous thought experiment, Schrödinger's cat. In this scenario, a cat in a sealed box is both alive and dead until someone opens the box to observe its state. This paradox highlights the unsettling implications of quantum mechanics, the idea that reality itself might be probabilistic rather than deterministic. Despite its strangeness, quantum mechanics has been incredibly successful in explaining the natural world and driving technological innovation. Lasers, transistors, and semiconductors, all the building blocks of modern technology, are based on quantum principles. Without quantum mechanics, there would be no smartphones, no GPS systems, and no internet as we know it. Even medical technologies like MRI scans rely on quantum physics to create detailed images of the human body. One of the most exciting applications of quantum mechanics today is quantum computing. Traditional computers process information in bits, which are either 0 south or 1 south. Quantum computers, on the other hand, use qubits, which can exist in multiple states simultaneously thanks to superposition. This allows quantum computers to solve problems exponentially faster than classical computers. While still in their infancy, quantum computers have the potential to revolutionize fields ranging from cryptography to drug discovery. Yet, for all its successes, quantum mechanics remains incomplete. The theory works extraordinarily well for describing the behavior of particles at small scales, but it doesn't mesh with Einstein's theory of general relativity, which governs the behavior of massive objects like planets and stars. Physicists are still searching for a theory of quantum gravity that unites these two pillars of modern physics. Until then, quantum mechanics remains a theory full of unanswered questions. What makes quantum mechanics so fascinating is not just its scientific implications but its philosophical ones. It challenges our most basic assumptions about reality. Is the universe deterministic, as classical physics suggested, or is it governed by probabilities? Does reality exist independently of observation, or is it shaped by our interactions with it? These questions go beyond science, touching on the nature of existence itself. Quantum mechanics teaches us that the universe is far stranger and more beautiful than we ever imagined. It reveals a world where particles can exist in two places at once, where the act of observation changes reality, and where the future is not fixed but full of possibilities. It's a reminder that even the smallest discoveries can have the biggest impacts. As we continue to explore the quantum world, we are not just uncovering the secrets of the universe, we are reshaping our place within it. Whether through groundbreaking technologies or profound philosophical insights, quantum mechanics is a testament to the power of human curiosity and the endless potential of scientific discovery. If you enjoyed this video, don't forget to give us a thumbs up and share this video with fellow space enthusiasts. Your support helps us continue exploring the wonders of the universe. Be sure to subscribe to SPACEEFIED and hit that bell icon so you never miss an update on our latest discoveries. Dive deeper into the mysteries of space by checking out our other videos, and let's keep the adventure going on together.